Hey, I had to be away for a few days doing other things like teaching and editing manuscripts and proposals and discussing things with students and collaborators live. So this is a Sunday morning, very nice weather outside, a bit hot, but I thought I'll squeeze in a podcast before I go out. Comparison of, so we are talking about contrasts and commonalities between Antarctic and Arctic sea ice. We had one podcast already. This one is going to be from this same paper, and then maybe I'll have another one from another paper. Since the responses are so different, and since both polar regions have so much impact on global climate, and of course, you have huge things to lose if you lose all this sea ice in the Arctic or in the Antarctic, Southern Ocean, and you have glacier melt going on, icebergs, uh, ice shelves carving off, and so on. We have to monitor these things closely, understand them, predict them, project their future, and so on and so forth. So this is comparison of historic submarine and modern satellite observations showing dramatic declines in Arctic sea ice thickness since the 1980s. So submarine data has been released. Navy is used to collect a lot of data. At some point, they realized these data are too important to be put away as classified documents. This is a very sensitive region, right? If sea ice does disappear, we learned about the times of the dinosaurs, the hothouse when there was no sea ice, no glaciers around. So you had a lot of biology, lush green forests in the polar circle, dinosaurs running around. So you have a lot of fossil fuels potentially buried in the sediments or in the ocean here. And every country around, and even country that's not in the immediate neighborhood, has strategic interest in the Arctic, and they may be salivating at the idea of Arctic sea ice disappearing, right? So on the other hand, it's not good for the overall Earth system. So regression analysis of the submarine record has been used to extend the data a little bit backward. Essentially, a lot of the data starts in 1979 as far as satellite records are considered, but you can see that ISAT and Cryosat 2 are here only short term. You can see, excuse me, I always do this. It's very humid, and when you start talking, you get thirsty, throat gets dry, and I always forget to put my tea here. So let me continue. Uh, Remember, we have to worry about the sea ice thickness and the extent. The extent is easy to monitor. Thickness often needs in situ data, like uh, submarine data, right? So I won't go into the details, but you've already seen this bad news in several places. February, March regression analysis, October, November. Why do we worry about these seasons? Because February, March is when you're coming out of the northern hemisphere winter, and what remains there is or what has grown is very critical. Obviously, it's higher than the October, November thickness in meters, and you can see it's continuing to drop here, but some intra-annual variability there. You have to be careful about trends versus intra-annual variabilities. This seems like a continuation, but this could be something else. But you always also have to be clear to see if there is a multi-decadal variability that we are confounding with trends. This is always tricky, right? So what is the risk? That's what you have to eventually worry about. Okay, so let's move on here. This is the caption for this. Changes in thickness and ice motion over time. Decreases in Arctic sea ice age, a proxy for ice thickness. So the older the ice, the thicker it is likely to be. Between the periods of 2007 to 2016 and 1984 to 1993, overlaid with May to September ice motion trends and trends in mean sea level pressure from 1984 to 2016. Decreasing pressure trends are shown in blue and the positive pressure trends are shown in red. Thick black contours indicate the mean extent of sea ice that is 3 or more years old during the early and late periods, and so on and so forth. So here we are again being brief. You can see decreased pressure trends in some places, which with a strong indicator of winds, pressure gradients doing certain things, ocean currents, ice drifts, flowing out of the Arctic and so on. And here you have change in ice thickness, so you can see there is a positive trend, ice drift speed, change in year, ice year, for example. Sorry, so just be careful of the colors. Ice drift speed that we read in the caption. So you can see how they are changing and how the extent is also changing. And you have uh, decreasing pressure trends here, increasing pressure trends here, and mean ice extent. This is the trend in ice thickness in centimeters per year. There are places where it's growing either by accumulating or, you know, they collide together and grow. What did we call it? You go and look it up, right? Sorry about that. So the trends of ice drift speeds are in 0.25 kilometers per day per year. So that's kind of the interval. Sorry. Again, so pressure trends here, increasing and decreasing pressure trends. Okay, so the change between two periods and the trends. What do you do with this? Basically, you can see that in the Antarctic, it's still a very complicated story as opposed to the Arctic, which is semi-enclosed, and you can see the contrasts and the commonalities that there are changes in sea level pressure, which is expected with global warming, right? And wind responses are also expected, but the Southern Ocean and the Antarctic are complicated by the ocean that is a channel that we cannot say enough times. And you can see you can be pushing ice out of these smaller. This is a complicated region, right? We saw the Amundsen Sea, Ross Sea, Weddell Sea, and so on. And you have the outer Southern Ocean that's doing its own thing. The subpolar front, subtropical fronts are moving around, and there's a complicated circulation in the vertical with the Antarctic bottom water, Antarctic intermediate water, and the North Atlantic deep water coming up, and so on. So the vertical structure is generally less favorable for sea ice formation, as we already saw. Make sure I'm not saying it incorrectly. So again, just remember the contrast. This is what we are mostly focused on, and there are lots of details on the mechanisms. Comparison. So next up here is comparison of modern observed and historical trends and variability of sea ice extent along with selected global climate model historical and projected trends from the World Climate Research Program's CMIP 5, which was the previous version. I'm a little bit behind on recording these, but also newer versions have not come. People write these kinds of reviews, contrast papers keep getting published, so I keep taking the latest paper, but you can see the data is a few years behind, which is common, and the projections are from the last version. Currently, we are in CMIP 6, which was released over 21-22. Okay, so just again, Arctic March and Arctic September. You can see that the crash here is faster. This is estimated from 1920 and projected into 2060. And the zoom in area for 1980 to 2000 shows the drop with lots of intraannual variability here in the ice extent in millions of square kilometers for the March period. So coming out of the winter, there is much more variability. If you have less ice coming out of the winter, then you can expect that it will not grow in spring and summer, and it will start to melt in fall and winter. It will melt during spring and winter, and the extent in September, as we said, is critical because that's what can refreeze during fall and winter. Antarctica, on the other hand, September and February, remember the seasons are reversed because it's a southern hemisphere, and you can see it's been argued that there's been some increasing trend, and more lately there's been a decreasing trend. But you can see that the projections are that we are going to drop even in the Antarctic sea ice extent in millions of square kilometers, and the uncertainty here, the range is high. This is the climate model range, which is high here as well. So they seem to converge uh, in these regions where we have good data. Sometimes models are good at producing the answer when we know the answer. And the projections, the trick, of course, is to remember that we are always um, full of uncertainty, and uncertainties are dominated by internal variability and model uncertainties in the first 1 or 2 decades. After that, scenarios that we use tend to dominate the projections, which I've discussed elsewhere that you can look up. So that's for September. So again, the coming out of the summer, it's sorry, this is coming out of the winter, and this is coming out of the summer. You have to adjust quickly to the two, and there are some proxy records put in as well. Okay, so same story, that there are contrasts and commonalities, and the main thing to remember is that this is a very sharp trend both in March and September, end of winter, end of summer. Here, end of the winter, not so strong trend, but projected in disappear. Sorry, and coming out of the summer, the trend is again not at all as strong as here, but the patchiness, you should always remember the patchiness of the Antarctic story, because there are places where trend in thickness is fairly strong and negative, whereas in other places it's positive. Okay, that's what we expect when we have such a strong ocean that is completely encircling the region. Contrasts and commonalities, then the changes in sea ice between the Arctic and Antarctic are a study in contrast. The Arctic has experienced dramatic and consistent losses of ice extent, thickness, and volume over the past several decades, while in the Antarctic the picture is one of regional and temporal variability. But this contrast can plausibly be attributed to an expected response due to both differing role of various processes that are ultimately controlled by contrasts in geography. Southern Ocean is a key player in the Antarctic story, and Arctic, of course, has a lot of Atlanticization and invasion of Atlantic water being one of the major stories. Secondly, the differing role of key processes that drive an amplified response to anthropogenic forcing in the Arctic and a more muted response overall in the Antarctic. But despite a growing understanding of how both forced and natural variability are driving uh, in changes in both regions, current climate models cannot robustly capture these changes, limiting our ability to project future changes on decadal timescales. Okay, that's what I said when I talked about model uncertainties, internal variabilities, and scenario uncertainties depending on how far you go into the future. Given the contrasting changes in sea ice in the north and south, are there connections and commonalities between the two? First, we've seen the important impact that modes of natural variability have on the ice cover at both poles. There is emerging evidence that ice extent in the Arctic, as has been well established for the Antarctic, is governed partially by natural variability that may originate from the tropics. Although this variability manifests differently at each pole due to differences in geography, evidence is emerging that wind-driven variability and ocean feedbacks, such as the ice albedo feedback, act in concert to drive sea ice trends. Ice albedo feedback is a strong one in the Arctic. We also know there is a cloud water vapor feedback. Still, the full story is not emerged as such. Moreover, as the Arctic ice cover continues to shrink and thicken, multi-year ice continues to disappear. The Arctic ice is becoming more like the Antarctic. In 2012, for instance, the summer minimum extent in the Arctic matched that in the Antarctic for the first time. The thinner Arctic ice is more dynamic, with more fractures and changes in the role of deformation, increasing the fluxes of heat and moisture from the ocean. As the open water fetch increases, the impact of waves and storms on the ice cover will become more important, and changes in ocean heat through both isolation and increased intrusion of subarctic waters into the Arctic Ocean may enhance the ocean heat supplied to the base of the ice. Furthermore, increased poleward heat and moisture transport in the Arctic may strengthen linkages to lower latitude modes of variability. So when you have things like El Nino in the low latitudes or even monsoon variability, it's been shown that waves can go all the way into the Arctic and produce heat waves and so on. But also remember, the key point here is that when you have ice cover, it's a very good insulator for the ocean. So ocean doesn't lose heat, which means you can freeze, produce more sea ice. But if a slight bit of crack or opening happens, since the atmosphere is colder, it can pick up lots of heat. Of course, atmosphere is warming because of the warm moist air intrusion, so the heat loss is reduced, but still the contrast between ice covered versus open ocean is going to be very strong. Okay, so keep all those details in mind. Despite an emerging understanding of the observed changes in the sea ice cover over the past 4 decades, it is clear that the response of the ice to both forced and natural variabilities are governed response is governed, sorry, by complex interactions and feedbacks among the atmosphere, ocean, and ice. Our ability to predict future changes in sea ice rests on improved understanding of the role of these interactions and feedbacks, particularly the role of natural variability. Many of these processes, such as ice-ocean interactions and feedbacks, are poorly observed. Improved understanding will require a sustained network of both satellite and in situ observations of these interactions as the ice cover continues to change. Okay, so that's the main story there for the Arctic and Antarctic contrasts and commonalities in sea ice. The big story is that the Antarctic is very different because the Southern Ocean is a channel and it can take up much more energy because there are no boundaries from the winds. It can take up much more energy, and if it warms, those currents can take the warming much deeper into the bottom of the ocean, to the bottom of the ocean, and that those warm waters can invade the Indian and Pacific Oceans as well as the Atlantic Ocean. The impact seems to be very clear on the Indian Ocean in terms of the heat balance because of this intrusion of Southern Ocean waters, and also in the Pacific, but much more contrasting in the Indian Ocean because it's closed off at low latitudes. Okay, so it's a nice story that just remember those differences. Polar amplification in the north, very obvious. Polar amplification in the south, not so obvious. Okay, so let's leave it here.